Hello everyone. Now in this lecture we will understand the priority scheduling, a solved example, and this question is asked in the GATE 2017 paper. Now I have taken this question from GATE 2017 and let us try to solve this problem and find out the average waiting time of all the processes using primitive priority scheduling algorithm, right? So now we have this table. So consider the following set of processes with arrival time in milliseconds. So CPU burst in millisecond, and the priority 0 is the highest priority, right? And none of the process have IO burst time. So they have clearly mentioned all this description, and they have asked us the average waiting time in milliseconds of the process using primitive priority scheduling algorithm is dash. Okay, so consider this table with having 5 processes. Arrival time is also mentioned, burst time is also mentioned, and their priority also mentioned. Okay, so 0 means the highest priority. Next one is the number 1, then 2, 3 and 4. So in this fashion we can execute these processes. Okay, so first of all we have to prepare the Gantt chart to resolve this problem and find out the average waiting time of all the processes, right? So they have mentioned we have to use the primitive priority scheduling algorithm, right? So in the priority scheduling algorithm we have to follow the primitive priority scheduling. Now based on the primitive priority scheduling we have prepared the Gantt chart, right? Considering the arrival time of the process. So the arrival time of the process P1 is 0, means it will occupy the CPU, right? It is executing for 2 millisecond, right? Because after 2 millisecond there is a one more process arriving, that is P4, right, which is having the highest priority than the currently executing process, right? So I request those who have not seen my previous lecture, go back and just see the lecture priority scheduling. There you will understand what is the difference between primitive and non-primitive. So in the priority scheduling we have primitive and non-primitive. In primitive, a currently executing process can be primed if the higher process enters. So now the highest process is entering after 2 millisecond. So after 2 millisecond the P1 has to suspend for a while, right? It has to terminate for a while. So now the process is interrupting, that is P4 process. So P4 process occupies the CPU, right? How long? The burst time is 10 millisecond, but here it is executing for only 3 millisecond. Okay, now consider it has executed for 3 millisecond. Okay, so it has left another 7 millisecond. Okay, now here also 11 minus 2 is 9 millisecond is the burst time of 9 millisecond is the burst time of P1. Okay, so why it is suspending, why P4 is suspending? Because after the P4 is executing for 3 millisecond, right, means at the 5th millisecond one more process is arriving, that is P2, and that is having the highest priority than other two, right? So this is the highest priority process P2. Now directly P2 will occupy the CPU at the 5th millisecond, right? And it will complete its burst time, right? So it has 28 millisecond of burst time. So already 5 millisecond has spent by the other two processes, means they have executed, right? Now P2 is entering and it will complete 28 millisecond and it will terminate at 33 millisecond. Okay, now after that again there is a P4 is executing. So after this 0, right, the next highest priority we can say that the number 1, right? This is P4. Again, P4 will occupy the CPU for how long? 7 millisecond, because it need only 7 millisecond. Already 3 millisecond work has been done, right? So P4 will execute for 7 millisecond. 33 plus 7, that is 40th millisecond. It will exit or completes its execution. It will come out from the CPU, and the CPU is allocated to next process, that is P1 process. So P1 is also executed for 2 millisecond. It need only 9 millisecond. So it will enter at 40th millisecond and it will leave the CPU at 49th millisecond. Okay. Now the next P3 process. So P3 is the third priority process. Okay, it will occupy, because we have only P3 and P5. So P5 is having fourth, means it is the least priority process. So the third is the highest priority process compared to P5. So P3 will execute. So what is the burst time? Only 2 milliseconds. So 49 to 50. So P3 will execute and it will come out at 51st millisecond, and P5 will occupy the CPU for how long? 16 millisecond, because burst time is 16 millisecond. So 51 to 16, that is 67 millisecond. So it will come out at 67th millisecond. So like this, all the process will complete their execution and burst time. Okay. Now, based on the priority scheduling and based on the arrival time of these processes, we have prepared this Gantt chart. Now let us consider the waiting time. So to calculate the waiting time, at the bottom you can see the formula. Waiting time equals to total waiting time, right? So the total waiting time of the process minus number of millisecond process executed previously minus arrival time of the process, right? So based on this formula, we have P1, right? P1, 40 is the total waiting time. So let us go to Gantt chart, and a last execution of the P1 started at 40th millisecond. So compared to 0 to 40, it is waiting for how long? 40 millisecond. Minus 2, what is this 2? Number of millisecond process executed earlier. So before 40, how much millisecond it has executed? It has executed 2 millisecond from 0 to 2. Okay, so 2. 0, what is 0? 0 is the arrival time, right? So it arrived at 0 time. So 40 minus 2 minus 0 is 38 millisecond is the waiting time for P1. Okay. Now P2, 5 is the total waiting time. So till 5 it is waiting, right? So 0, number of millisecond executed previously. So no previous history, right? So number of millisecond process executed is 0, right? Arrival time, that is 5, right? 5. So 5 minus 0 minus 5, that is 0, right? Next, P3 process. So 49 is the total waiting period. So how long it is waiting? So it is entering at 49th millisecond. So this P3. So 49 minus 0, what is 0? 0 is the number of millisecond process executed. So it has not executed before 49 millisecond. There were no execution of the P3 process. So number of millisecond process executed is 0. So arrival time is the 12, right? 49 minus 12 is 37 is the waiting time. Similarly, P4. So where is P4? Yes, here, right? So it is entering at 33 milliseconds. So 33 is waiting time. What is 3? 3 is the number of millisecond process executed. So it has executed here for 3 millisecond. I have already mentioned 3 millisecond, 2 to 5. Okay. So 3 minus 2. 2 is the arrival time. Here in the table we have mentioned. Okay. So 33 minus 3 is 30. 30 minus 2 is 28. 28 millisecond is the waiting time for P4. Similarly, P5, 51 millisecond. So total waiting period is 51 millisecond minus 0, number of millisecond process executed. So before it has not executed. So 0 minus 9. So what is 9? 9 is the arrival time. So what is the arrival time here? 9, right? So 51 minus 9 is 42 milliseconds. So this is the waiting time for P5. So after calculating all the waiting time for P1 to P5, let's go to average waiting time. To calculate average waiting time, we have to add 38 plus 37 plus 28 plus 42, right? So P2 is 0. So 38 plus 0 plus 37 plus 28 plus 42. So that is 145, which is divided by number of process, that is 5. So we are getting 29 millisecond is the average waiting time of these 5 processes. So in this, as we have calculated, 29 millisecond is the average waiting time, right? So in the GATE 2017 question, this was asked. This question was asked and they have clearly mentioned. So primitive priority scheduling algorithm we have to use, and we have to calculate the average time in millisecond, right? So 29 is the right answer. So in this fashion you can calculate the average waiting time of the process, whichever the algorithm we are using. So in the question they will mention the algorithm name, they will give the proper table. If in the table there is no arrival time is mentioned, so we can put it the arrival time as 0 to all the processes, and we need to calculate and find the right answer to it, right? So hope you understood this, right? So we will come up with another example in the next lecture. So see you in the next lecture. Thank you for watching.